So inhibitory channels, GABA and glycine, they're amino acid gated because GABA and glycine are amino acids. GABA mediates the inhibitory transmission, where glycine mediates the non-GABA inhibitory transmission. So I believe that means that it's inhibiting it's controlling other pathways which can inhibit these channels. And so you have this chlorine channel, and it's GABA gated. So I believe they're inhibitory, so GABA would close this channel. And they also bind other molecules to it that either in other sites. So they're antagonists. Right? Yeah. Non-competitive antagonists. That will affect this chlorine channel. So when you open the chlorine channels, you have inhibitory postsynaptic potentials. So before you were depolarizing the cell when you open the sodium channels, now you're hyperpolarizing the cell. You're making it more negative, making it more difficult to excite this spot. So here you're recording from just inside. You can see, again, it's not going to be a whole lot of voltage change, but it's enough to make a difference. Particularly when you sum up inputs from multiple neurons or multiple inputs from the same neuron. So they sum both spatially and temporally. If you have one action potential come in, you see the synapse, you see these are excitatory, so the voltage increases a little bit. If you have multiple neurons at the same time sending in an action potential, they add together, so you get a lot bigger increase in the voltage. So maybe that'll be enough to hit it over threshold and activate an action potential. Maybe it just gets it closer. Or if they come really fast in time from the same neuron, if they're close enough together that the potential is not dropped back to 65, the baseline, then they sum together in time. So you get a little, maybe over here you'd finally hit threshold. Not up here where you would. And this happens the same thing if they're hyperpolarizing the cell. Or maybe you're going to have a combination of inhibitory and excitatory that regulate the voltage level. So say you had a excitatory going down the dendrite, and this one is very large, where maybe the inhibitory synapse you're getting just a little bit. But what it does is they're very close to the soma, and they actually shunt the voltage out of the cell so that it leaves and doesn't activate. So if the inhibitory synapse is inactive, this excitatory potential travels all the way to the soma. And you can see there was some resistance, so it decreased. But if you take into account, now this is a closer amplitude to what an inhibitory would have. So when the inhibitory is activated, it cancels out that excitatory, and the soma doesn't receive anything. So now you put these all together, and you're going to get this very complex interaction between exciting and inhibiting the cell based on what message you want this neuron to receive. G-protein coupled channels are a little bit more complex. Instead of opening a channel, the neurotransmitter is going to go to a binding site, which releases this G-protein. The G-protein starts off a chain reaction. So maybe it releases something that opens an ion channel, or maybe it has a conformation change that affects an ion channel, or it releases some other protein or ATP or something, and it affects a channel, or even another enzyme that generates second messengers. And this is very slow because you have to wait for multiple proteins to react, but you can amplify your signal a lot. So one neurotransmitter, maybe this G protein opens a channel and activates an enzyme to send signals to the rest of the cell. Or maybe you're generating ATP and that's driving a whole bunch of different things. And here's a list of some G protein neurotransmitter receptors, or neurotransmitters and their receptors. So an example of a system that uses G proteins is the olfactory system, so your sense of smell. You have these odors, so here it's not a neurotransmitter activating it, but a particle that has a smell. And it releases a G protein that activates an adenylene cyclase. So it looks like it consumes ATP to make cyclic AMP, which now activates multiple channels, opens many channels so that sodium and calcium flow into the cell. And these in turn open chloride channels. And together you start depolarizing the membrane. So from one particle, one molecule, you get all these ions channels opened. And you can use that to mediate the pathway. This depolarization, either maybe it's enough to reach threshold, or it combines with these other excitatory depolarizations to activate the neuron. Another system that uses it is light transduction. So in your eye, when you're seeing things in your rods and cones, they have these discs. And so you start off with, when it's dark, you have an inactive G protein and sodium flowing in to your cell. But when light hits the rhodopsin, it activates the G protein, which causes stuff to happen. And you activate the phosphodiesterase. And you end up closing the sodium channel so that the cell can do what it needs to activate these pathways.